This is an airburst of a typical nuclear weapon exploded at a height of about 2,000 feet. The first observed effect is a brilliant flash of bluish-white light that overwhelms the vision of even distant observers. The ball of fire, an incandescent sphere of glowing gases whose internal temperature is measured in thousands of degrees, starts to climb into the sky. Ball, a fraction of a second old, has an energy equivalent to 20,000 tons of conventional explosive. Its internal pressure is measured in thousands of pounds per square inch. As the luminous fireball grows to its eventual 1,000-foot diameter, gamma rays and neutrons are released to produce their lethal effect. Thermal or heat radiation ignites inflammable materials and inflicts personnel burns at relatively long ranges. The blast wave separates from the fireball and, traveling faster than sound, moves outward to batter the target area. This pulverizing shock wave forms a dust pedestal which seems to follow the rising cloud, developing into the characteristic mushroom shape of a low-altitude burst. Losing brilliance rapidly, the fireball is colored an orange-brown by the release of oxides of nitrogen from the surrounding air. Turbulent and still glowing, it shoots upward with an initial velocity of more than 100 miles per hour. As incandescence disappears, condensing water vapor begins to whiten the cloud. At still greater heights, ice crystals form and flow over the edges of the cloud to form a pure white color. Under certain atmospheric conditions, an ice cap may form above the cloud. Eventually, this cloud, with a diameter of about 3 miles, may reach an altitude of 50,000 feet. Then, slowly, it drifts away, mingling and blending with the clouds of the air until it can no longer be identified by the human eye. The destruction caused by a relatively low-yield weapon can result in many square miles of ruins and account for thousands of human casualties. But how did it all come about? What caused this destruction? What can we do to increase the destructive effect? Or conversely, how can we protect ourselves from it? Generally speaking, the main damaging effects of a nuclear weapon detonated within the atmosphere are blast, heat, and nuclear radiation. To add to our knowledge of the blast effects of a nuclear detonation on structures of known strength, an extensive test program has been carried out. Here, remotely controlled cameras record the impact of an atomic blast. Such a shock wave has a very long duration compared to that of conventional explosives. An atomic shock wave can envelop a structure and completely destroy it by pressure and dynamic wind effects. The damaging effects of the shock wave are maximized by a phenomenon called the Mach stem. This is a reinforcement of the blast wave by a reflected wave from the ground. This effect provides the basis for selecting an optimum height of burst associated with a particular yield to produce maximum destruction. With a higher yield of thermonuclear weapons, the distance at which destructive overpressure levels can extend and the duration time of the overpressure are increased to greatly extend the area of damage. In our tests, the Mach stem has been used against every type of structure: masonry, steel frame buildings, reinforced frame buildings, and wood frame construction. The side-on pressure, which hits a large building, can build up several times the pressure level occurring in the open. This is caused by the air piling up against the building. A secondary but very important aspect of blast effects on buildings and structures is the number of exposed and unprotected persons who will be killed or injured by the flying debris produced by the passage of the blast wave. This blast wave has a double destructive effect in that it is lethal to not only city structures, but also to a city's people. An interesting phenomenon in connection with the blast wave is called the precursor. It forms as a result of the heating of a surface layer of air by the thermal radiation. Light, although not a primary casualty producer, can cause temporary flash blindness to unshielded eyes. In addition, anyone looking directly at a nuclear explosion may suffer permanent eye damage even at very large ranges. Readily visible, day or night, the intense flash of white light is an easy identifying mark of the nuclear burst. No other type of explosion can equal it. Thermal radiation starts fires and causes serious burns on unprotected or lightly protected skin at long ranges. The combination of fire kindling and casualty producing capabilities makes thermal radiation the most damaging single weapon effect against urban targets. As seen in these remote camera views, ignition of easily flammable fuels is almost instantaneous. Skin burns occur with similar speed. In most cases, evasive action from the brief flash of heat cannot be accomplished. However, anything that casts a shadow will afford some protection from this flash of heat. Ordinary clothing, as light-colored and loose-fitting as possible, offers excellent protection at distances greater than 1 mile. With an inflammable target, primary fires join with secondary fires caused by ruptured gas lines, electrical short circuits, and the like, to form a conflagration which may multiply the initial damage many times. In wooded areas, there is a possibility of starting forest fires, which might have a great effect on tactical situations. In an airburst, radiation is not the most serious consideration. Here, the largest percentage of the radiation is carried off by the nuclear cloud and dispersed throughout the upper air, presenting no problem to troops on the ground. The initial nuclear radiation is half over 1 second after detonation, and all over in from 10 seconds to 1 minute after the appearance of the white light. Penetration of initial gamma radiation is reduced by dense materials, 1 1/2 inches of steel, 6 inches of concrete, or 7 1/2 inches of ordinary dirt will cut gamma radiation by 50%. Take cover is the best philosophy for protection against nuclear radiation as well as from blast and heat. Even in this nuclear age, the foxhole is still the soldier's best friend. Although the airburst weapons comprise the largest part of our stockpiles, underwater, underground, and surface burst weapons also play an important part in military planning. As a part of the test series, underwater bursts were conducted against an array of target ships. Since the fireball is beneath the surface and the thermal radiation is absorbed by the water, there is no surface thermal effect. When the explosion bubble vents through the surface, an outward traveling shock wave is formed in the air. However, there is no augmentation of pressure by the Mach stem as in the case of an airburst. Significant from a military standpoint, however, is the tremendous column of water thrown up by the detonation. This water traps the fission fragments and is irradiated by the neutron flux. When the column rains out in the target area, it contaminates the target. The violent underwater shock makes a nuclear weapon capable of underwater detonation extremely effective against ships and submerged submarines. In the case of surface vessels, the surface water wave may also be destructive. In some aspects, the effects of an underground detonation are similar to an underwater burst. As in the case of an underwater burst, there are no direct thermal or nuclear radiation effects on surface targets. The air blast is somewhat lower than from a comparable surface or low airburst weapon, while underground shock is maximized. Most of the radioactive fission fragments are trapped in the dirt. Thrown up by the explosion, radioactive particles fall out on the target area, creating dangerous surface contamination. As in the case of the underwater detonation, this residual radiation will tend to restrict occupation of the area for a considerable length of time. A weapon with a yield around 20 kilotons, burst in dry soil 50 feet below the surface, will produce a crater approximately 650 feet in diameter and 140 feet deep. This cratering action, plus residual radiation, effectively denies the area to personnel, making an underground detonation effective against specific targets, including underground structures. The surface burst has some characteristics of both underground and air bursts. In a ground level burst, the thermal effect may be degraded due to absorption by the ground and the dust skirt. Blast overpressure, however, is much greater than with the underground burst. Residual radiation, being so much greater than the militarily insignificant amounts left after an air burst, contaminate large areas and have a definite effect upon tactical situations. The crater made by a surface burst is sizable, although its dimensions are much less than those from an underground detonation of comparable yield. All types of nuclear bursts must be evaluated, since each type has specific areas of greatest effectiveness. Residual radiation to contaminate areas. Blast to destroy structures. Thermal and nuclear radiation to kill personnel. A nuclear weapon represents potentials outside the concepts of conventional weapons. But this is not an ultimate weapon, nor one calling for unreasoning fear. It is merely another arm, another addition to our national arsenal. With prompt action, based on a thorough understanding of nuclear effects, our chance for survival in a nuclear war can be greatly increased.